is spinning. Linear motion is very easy. If I'm moving here and the global coordinate is also moving, and that's coming from the relative motion, you already know how to do it. That's very simple. But what if the reference frame, the global reference frame, is not stationary, it's also spinning and also moving? How do we put these two together? And that's how we're going to use Euler series to solve this kind of problems. But before we start with an example, let's run a quick review to connect all the dots before we apply them to example 31. Remember at the beginning of this semester, I promised you to show you the structure of all the motion to convince you that everything we talk about in dynamics, all the subjects are part of one system. And this is another attempt on three-dimensional general motion. Now, let's consider, well, we choose the plate, so let's consider the plate. Suppose we have a plate like this. And let's consider 2 points. One is at the center, so we can call this point A, and another point is at the corner. So this here is point B. Now, if this plate, three-dimensional plate, is in linear motion, which means that at the center, we will describe the linear velocity and linear acceleration, as well as linear displacement at the center of gravity. In this case, point A is at the center of gravity, because it's obvious. Of course, we assume that density is unit, is constant. That means here you have provided with the VA as well as AA. Of course, point A is at the center of gravity. If I'm not being clear, at G, point A is at the center of gravity. Now, if you know the velocity at point A, which is at the center of gravity, what about the velocity and acceleration at point B? In this case, it's the same, right? It's going to be the same. So from here, we know that VB is just VA. AB is just AA. When there is no angular motion, linear motion. And please keep in mind that this velocity doesn't have to be horizontal. It can be in any direction. It can be going this way or going this way. Doesn't matter. Velocity and acceleration doesn't have to be horizontal. So that's case 1. And case 2 is when we start considering the motion of the plate in the angular domain. So the same thing, we still consider B here. This is still point A. Now we have to start considering rotation. And to do that, you certainly have to establish a three-dimensional coordinate system, because when we deal with angular quantities, they always are in the vector form, and there's no better way to describe these angular quantities without establishing a three-dimensional coordinate system. So let's consider that at point A, I don't want to make this horizontal, so you will think that this has to be horizontal. It doesn't have to be. So you still have VA and AA, right? We still have this, and we also established XYZ like this. Now I'm going to spin it. So I'm going to spin it with respect to the z-axis. So this is my omega. Of course, you know that omega must be described by what? By angular velocity. Now, of course, I can also say that there's also an angular acceleration in the same direction. So the difference between these two, in the linear motion, you know that everything is just the same. Whatever the velocity and acceleration you are provided at the center of gravity is the same velocity and acceleration everywhere else. That's the case when there's no angular motion. Now, when you have angular motion, how do we find out the linear velocities? When we have this part that we did before. So here, Now, if I have not only the linear but also the angular motion, VB equals to VA plus, what's this? Omega cross RBA. So what's RBA? RBA is this, from A to B. This is RBA, right? So the difference between these two now is obvious because it has an angular component right here. And what about AA? I'm sorry, AB. What about AB? For AB, it is, of course, there's always in relative motion, of course, because it's moving relatively. B is moving relatively with respect to point A, and A is also moving. So you must consider the AA first, right? And there are also two other components. The first one is plus alpha cross RBA. This is what we call the tangential component of linear acceleration in relative motion. Minus omega squared times RBA. This is the normal component. Okay, so if you want to know why these are like this is the tangential, this is the normal. By what? By ignoring AA. So if you consider that, before I consider the linear acceleration at point A, I just consider the whole thing is only spinning like this. So at this point, the tangential linear acceleration is determined by this expression. And the normal linear acceleration is determined by this calculation. We talked about this before. But by listing all these together, you see that if you have one omega and one alpha, this is how you're going to complicate your calculation. Without these omega and alpha, they are the same, just like before, right? Okay, now let's add another thing, case 3. So what is case 3? Case 3 is, of course, we can make this problem more difficult or even more interesting, but let's just consider this. We have x, y, and z, like this. Now, I have one axis. Suppose that this whole thing is spinning with respect to a I'm going to call this omega 1, this one omega 2, like this. Now we have two angular velocities, right? So how are we going to calculate linear and also a linear velocity and linear acceleration? So here, first of all, according to Euler theory, the angular velocity at this moment when you consider this two, at that moment, the total angular velocity is the sum of these two. And this is the part I warned you earlier. Despite of this simple expression, the physical implementation is crucial, because that means that this linearity only applies at that instant. However, for angular acceleration is not just the linear superposition of these two. For angular acceleration is actually the time derivative of the first one individually plus the time derivative. The first one is omega 1, put the dot, that means the time derivative. And also the time derivative of omega 2 plus the cross product between these two. So this is the difference when you have two angular velocities. Now, how do we calculate linear ones? I need a space, so I'm going to erase this part. Yeah, actually, I'm going to erase this part.